Alright, so in this video I'm gonna be explaining another important article, and the title is Deep Domain Generalization with a Structured Low-Rank Constraint. This approach, this idea is a little bit similar to the idea of previous video in part 73, but they use a different formulation, a different way to learn the functions. So this paper in 2018 from IEEE. Domain adaptation nowadays attracts increasing interest in pattern recognition and computer vision field, since it is an appealing technique in fighting off weakly labeled or even totally unlabeled target data by leveraging knowledge from external well-learned sources. Conventional domain adaptation assumes that target data are still accessible in the training stage. However, we would always confront such cases in reality that the target data are totally blind in the training stage. This is extremely challenging since we have no prior knowledge of the target. So in domain generalization, we assume that the target is unseen, but in domain adaptation, we can use the samples, not the labels, the samples of the target. So we develop a deep domain generalization with a structured low-rank constraint to facilitate the unseen, or some people say unknown, target domain evaluation by capturing consistent knowledge across multiple related source domains. Specifically, multiple domain-specific deep neural networks are built to capture the rich information within multiple sources. Meanwhile, a domain-invariant deep neural network is jointly designed to uncover most consistent and common knowledge across multiple sources so that we can generalize it to unseen target domains in the test stage. Moreover, structured low-rank constraint is exploited to align multiple domain-specific networks and a domain-invariant one in order to better transfer knowledge from multiple sources to boost the learning problem in unseen target domains. So we have multiple sources and we have this unseen target. We want to transfer the knowledge from sources to this unseen target. And the architecture is very beautiful. You see the domain-specific deep neural network, E sub I. So they come from different domain I, domain J. And then we have this low structure, low rank. And at the same time, we have domain-invariant deep neural networks that we can classify, and you can use it for unseen target domain. So the domain-invariant deep neural networks is learned here, and the domain-specific neural networks is learned here. But what can merge and deal with these things is this structured low rank. So domain can be defined as probability distributions. The main difference between multi-source domain and domain generalization is the accessibility of the target data. So we have discussed this several times. We desire to explore deep structured learning in domain generalization to uncover more effective knowledge across multiple domains. Considering the distribution divergence among multiple sources, we design multiple domain-specific deep structures, multiple domain, and each one for one source domain to transform multiple sources into latent space. So now they are in the latent space, because each one has its own domain specific of domain 1, domain specific of domain 2. And then what we do is here. Specifically, each domain can be treated as one task in multitask scheme. And Yashio Bengio here mentioned that good representation should have such prior as shared factor across tasks. Therefore, we assume different networks should have similar activation values given the same class of objects from different domains. And our domain invariant on the right was domain invariant. This one, domain invariant, is designed to capture most shared factor across tasks. Such domain invariant deep structure is treated as an approximation of the specific target domain deep structure when we cannot have access to any target data during the training procedure. And to build a deep domain generalization model, we extend the well-known architectures which are comprised of several computational layers, a few fully connected layers, and generally each fully connected layer learns a nonlinear transformation. For our model, the inference is provided with y hat. And y hat is the task-specific label prediction. So we want to minimize the loss function with respect to these parameters. So this is the total loss function. So the first one is L sub g, which is classification loss. L sub d is just a network difference loss. L sub r is the reconstruction loss. The classification loss, everybody knows, we do it every time. It's just cross entropy, the negative likelihood of the ground truth. And the cross network difference, this one, D stands for difference, cross network difference. You see the difference? Is also exploited to all source domains and encourages the domain invariant network to preserve most information across multiple domain specific networks. Since multiple sources all share the same categories but in different distributions, we assume the domain-specific deep network share most information in the latent space where the knowledge can be extended to unseen target domain. So each domain-specific network can be treated as one task. It has been suggested in 24 that good representation should have such prior as shared factors across tasks. So we assume that different networks should have similar activation values. The reconstruction loss is also applied to encourage the shared and private networks to capture more discriminate information. When the domain distribution difference is mitigated with deep architecture, we could observe that within the class data would gather together although they are from different domains. That is, each sample would be highly similar to other samples in the same class. In this way, the conditional distribution difference could be addressed. Therefore, we explored the structured low-rank constraint could help transfer knowledge from domain-specific networks to domain-invariant networks. So H sub I and its HCI be matrices whose rows are the domain-specific representation and domain-invariant representations. from the samples of the I sources. To guide two types of network learning and adapt more effective information to unseen target data, we adopt low-rank reconstruction to couple the output of each domain-specific network and the output of the domain invariant. So there is a constraint that we can relate H sub S to H sub C. But we want this matrix that is multiplied by that to be minimum rank. So Z is the reconstruction coefficient matrix and rank is the rank operator. The rank minimization issue can be addressed in the form as a good surrogate. Actually, the low-rank reconstruction matrix, this Z here, tends to be block diagonal in the ideal case, since only the within-class data are correlated across two types of deep networks. Similar ideas were proposed in the literature, which adopted multi-view data to reconstruct each view under linear transformation with low-rank constraint. So previous model works in an unsupervised way, which still treats the dataset as the whole and ignores the discriminative information during low-rank construction. It is hard to recover block diagonal low-rank matrices. So we propose to guide low-rank through structured matrix across two types of deep networks. Q is the structured low-rank, which is defined like this, that if H, S and C belong to the same class, then Q is 1, otherwise is 0. The motivation is here. Clearly, Q is a block diagonal structured matrix because it is constructed based on within class relationship. Such structured low-rank reconstruction would involve more label information during deep structures learning so that the conditional distribution difference across two types of deep structures could be reduced. To that end, we develop a novel loss function for deep domain generalization with this constraint. So this Q is a structured matrix that is defined like that, and we go from HC, we multiply it by Z, it becomes H sub S. And of course, for different classes, we have different rows. Now, that equation is challenging to be addressed because of the nonlinearity and non-convexity. We present an alternative optimization to iteratively update the two sub-problems. The first sub-problem is optimizing the low-rank coefficient. The second one is learn two types of deep structures. So the first one, we propose to update low-rank coefficients, then provide the deep structure optimization. When the deep structures are fixed, the objective function degenerates to traditional low-rank modeling problem. Then we drive the corresponding augmented Lagrangian function with respect to Z. And R is the Lagrangian multiplier. Mu is just a penalty. And this one is an inner product of two matrices. So Z can be obtained as this one. This is the Lagrangian augmented, not a Lagrangian, it's an augmented Lagrangian. The multiplier R and a penalty are updated here. After Z updated, we could adopt conventional gradient descent strategy. Then they have some data sets like this Office 10 and then Caltech 10. But this data set is very popular. This Amazon Webcam DSLR Caltech. So because we are doing here domain adaptation, we go from source to target. But this paper is about domain generalization, so we can just see what happens to the unseen target domain. This is the cross-recognition accuracy of 9 algorithms on this VLCS dataset. Red color denotes the best recognition rates.